Need to remember to record. Okay, so we're recording right now. Let's just get started. As you guys are here, and I don't want to waste your time. So we'll go through a few things. So this is going to be week one, part two. We've already covered some of the basics in terms of the course outline. Now you guys are in uh, sections 401 and 402. And And essentially, good morning, Jeremiah. Essentially, what you're going to be doing is having your Thursday class, which is not really a Thursday class, but I'm going to be recording it on Thursday. And then hopefully by late morning, the recording will be available unless you want to attend live. And then Monday, approximately 8:30-ish to 10:20, I want to record again. So this one was what, 9:30 to 10:20 a.m. This way, if people want to pick up shifts, if they want to go to work, if they have other things to do for the rest of the day, they're welcome to, or they can attend it. The only time I'm going to ask that everybody be here so that they can take test number two, test number one. That's the only time. Why? Because I want to watch, right? I just want to make sure everybody takes the test alone. Now, again, there's no requirement, there's no one time. So what will happen is that I'll give a few options for people to write the test. Okay, now going back to the assignments, I know this is important for you to know how you're going to attain the marks in this course. I know that's always important for me when I'm attending a class. So the main method of attaining is through assignments that are in supposed to be in-class assignments, but you guys really don't have an in-class situation. So what's going to happen is you will have time. The lectures will be accordingly, so you'll have time to work on the assignment. Now, those of you who attend class regularly, the recording session, I'll stick around to answer your questions. And in the first half, you will have, so in the first half, you'll have assignments 1 through 3, okay? And you'll have test number 1. Now, each assignment is worth 5% of your course for a total of 15%, and the test is worth 25%. So by the time you are set up with the other professor, because I'm off in July and August, your test will be, your test and assignments will be 40% already done. What I'm going to ask you guys is, because the first half is a little more straightforward, I won't say anything is easy in this class, but it's more basic concepts. So a lot of this testing is on the basics. So the more of this 40% that you achieve before the second half, the better. Because when you get into, so right, like for example, right now it's the basis of forces and gravity. But the more you get into the moment of gyration, trying to determine the center of gravity, you know, that's going to be in the second half of the course. It's a little bit more complex. So getting that 60% or getting the marks that you want in the second half is a little more challenging. So what I'm going to say is try to get as much of that 40% as possible, ideally 35 plus, so that you're in a good place to pass the course in the second semester, right? Another question I usually get from students about this course is, do you have to be geniuses or whizzes in? Do you have to be whizzes in math or physics to be an architectural technologist or architect? The answer is no. But you do have to pass the course. And because this is something that stresses people out, I do try to give you guys the opportunity to secure as many marks as possible. Because in the second half of the class, you'll still have 2 tests, which are always stressful, and 2 assignments. Okay. But one way to enhance your chances is to attend the classes, or in your case, in 40142, view the recordings regularly. And those of you who are not attending class synchronously, which you don't have to, and you're watching the recording, I would say set up the same weekly schedule, weekly time. And there's great tips available on the internet about how to do that. Now, talking about this topic about, do you need to be good in math or not? I have a question for you guys, and I'll give you guys a few seconds to think about it. What is the language? What is the language of physics? Because we're studying physics, right? So what is physics? What is the language of physics? If somebody came to you and said, what do you need to know to understand physics? What would you say? So
At booking.
What I would say the language of physics are numbers. And what kind of numbers should we use in physics? What kind of numbers should we use in physics? Should we use Roman numerals? Do we use Greek? Egyptian? What type of numbers should we use? Or do we use? How about Arab? Have you guys heard about what type of numbers we use? What are they called? This is an interesting story that I like to bring up with students, along with a few others. We actually use what are known as Arabic numerals. But are they truly Arabic? Not really. Why? Because they're actually Hindu, Indian, developed by Persians or Persian, and made popular in our culture or what the Western world by an Italian. So it was truly a global effort. But the dominant culture of the time was Arabic speaking. So that's why they're known as Arabic numerals. So let's watch a short clip because, you guys should know what language you use for physics and where did it come from? The language of math or the numerals that we use. Okay, hold on. Let me make sure that I've optimized it so that you can get sound. If you don't get sound, let me know.
.com. We're more than just hotels. We're tree houses.
Are you getting sound?
Yeah, I could hear it.
Thanks. Appreciate it.
To much of the world, he was known by his Latin nickname algorithmi, which became the origin of the word algorithm. He pioneered a method for solving problems called algebra, today known as algebra. 1,200 years ago, he published the first atlas of the known world, wrote the first math textbook, and was calculating the movement of celestial bodies when Europeans were basically staring up the sky through toilet paper tubes. His name was Abu Abdallah Muhammad ibn Musa al-Khwarizmi, but you could just call him al-Khwarizmi, the man who made possible the math.
So I just wanted to point something else out.
Call him al-Khwarizmi.
So he was honored by the Soviet Union because he came from a part of the Persian world, or the part of the area of Central Asia that was a part of the Soviet Union under Russian domination at the time. So that's why you'll see people like him are honored by the Soviet Union, or at the time it was the Soviet Union. Now it's Russia.
The man who made possible the math we use today. Oh, also including all the numbers that we use. Though his most lasting legacy was introducing so-called Arabic numerals to much of the world, he wasn't an Arab. He was most likely Persian. Born in what is now Uzbekistan around 780, Al-Khwarizmi first appears in historical records as an instructor at one of the great ancient Islamic learning institutions, Baghdad's House of Wisdom. Sounds kind of like a theme restaurant owned by celebrity nerds. The House of Wisdom was actually a crossroads of the great civilizations of the ancient world: Babylon, Greek, Hindu, Arabic, Persian, and Al-Khwarizmi liked to wet his beak in the knowledge that each had to offer. He studied the ambitious math of the Greek scientist Ptolemy, for example, who had tried to measure the world. But Al-Khwarizmi discovered that Ptolemy's calculations were wrong, so he corrected and reorganized all the data with new coordinates.
By the way, the people of this era, which I've studied before, they really, really looked up to the Greeks, the ancient Greek philosophers and thinkers. I just thought it was very interesting how these guys idealized them as, this is the way to move forward as humanity, the ancient Greeks.
With the help of some 70 geographers under his direction, he compiled a book called The Face of the Earth, a complete explanation of the geography and cartography of the known world, thought to be the first of its kind. He was also the official astronomer of the court in Baghdad, and as part of his duties, he compiled charts that tracked the moon and 5 planets. These tables turned out to be so useful and accurate that centuries later they would be translated into Latin and Chinese and circulated around the world. But his real passion was for mathematics, and he eagerly accepted a commission from Muslim leaders to come up with a...
Well, that commission was possible in that time because their religion, the religion of the area where he lived, it says that that if you're about to die and you leave some of your money to do something that creates knowledge in the world that benefits humans, your grave is like a piece of heaven. And so that was part of why a lot of these cultures developed what we now would consider tenureship, where there was funding for this kind of work, because especially people who had a lot more money, when they were about to die, their children would want to put aside some money to spread knowledge that would benefit humans. So I know we tend to look at religion as in a conflict with knowledge and science, but that's not always been the case. And interestingly, later on, a lot of the great philosophers and scientists and great thinkers of the Enlightenment, even in the Western world, many of them had their origin in the cloth, in religion. So I just thought that was very interesting how we should be careful about how we talk about the past. There is always some good that has come from our institutions, while we can also criticize that there's also some that we don't think that is applicable in the modern world. Or one could argue maybe it shouldn't have gone the way it should have, like the religious-based wars.
Text for the general public about how to do basic calculations, like for conducting trade and making measurements. The result was a text with the inimitable name, The Compendious Book on Calculation by...
This is very, very important, that when these guys developed methods where measurement became more systematic, it was extremely important because that's how trade was made more fluent and fluid between different cultures, civilizations. And as long as you have the ability to talk in math, that's the language that everybody can understand. Another concept, which I'll probably get into a little bit later, is when you have numbers, it's hard to dispute numbers, although some might. Like the president in the United States, he disputes numbers all the time, depending on what he's talking about. But most people who look at numbers objectively are going to understand that that number means a certain thing. Like, for example, you have quantitative and you have qualitative. So when you have quantitative, it's a quantity, right? It's a number. You could say that Sajjad is weighing 195 pounds. That's a number. And if we measure, we are going to have an exact same number. Everybody's going to get the same answer. But if somebody says Sajjad is a bad person, that's more of a qualitative assessment, right? Or Sajjad is a jerk, because it's hard to measure that. That's more of an interpretation of things that people observe or encounter in their dealings with me. You know, and people are going to have varying opinions of that. And so that's why I always find it interesting. It's wonderful to study science because you can have certain numbers and measurements that are exact. However, when you look into the other areas of our life and our existence, then it becomes a little more complicated. It becomes a little more of a discussion, whether it's quantitative or qualitative.
Completion and balancing. In it, Al-Khwarizmi explains how to solve linear equations and quadratic equations with what he called al-jabr, or completion, by subtracting or dividing an amount from both sides to find a missing figure. You know, solving for x. It's not that he invented algebra, though he certainly refined our understanding of it. Instead, he codified knowledge from a whole bunch of different traditions, especially Greek and Indian, to make life easier for the 9th century equivalent of English majors everywhere. In this regard, by far his most lasting achievement came from his study of ancient Indian texts. In 825, he published On the Calculation with Hindu Numerals, where he described everything he learned about Hindu mathematics. It was a weird system, with digits from 0, which meant, like, nothing, to 9, and it used decimal places to denote increments of tenths, hundredths, and so on. The book didn't exactly fly off the shelves of the Baghdad Barnes & Noble, but it would turn out to be one of the most influential books in history. Because 300 years later, a copy of it was discovered by an English monk who, fascinated with Muslim scholarship, translated the research of Al-Khwarizmi, now called algorithmi, into Latin. Soon, Europe's scholarly elite was eating it up. The Hindu system was way easier and more intuitive than Roman numerals, which used a base 10 for counting and a base 12 for fractions, and had no concept of 0. Men of science began advocating for the use of what became known as Arabic numerals, chief among them Italian mathematician Fibonacci, who wrote a whole book about them in 1202. But of course, medieval Europe, it wasn't really all about the new ideas with all the burning people at stakes in the Inquisitioning. In 1299,
By the way, the Inquisition didn't happen for a couple hundred years. That was more in the 15th century. Just keep that in mind. And that was, a lot of that was about getting rid of Muslims and Jewish people from the Iberian Peninsula. And that was post-Crusades.
the city of Florence, Italy actually passed a law forbidding the use of the numerals, not because of some anti-Muslim bias, but because Arabic numerals were just too easy to change. You could make a 6 into an 8, or throw a couple zeros after something and make a big profit with just a flick of the quill. It wasn't until the 1500s that the numbers began to take hold among merchants as well as scholars. But by that time, Al-Khwarizmi was forgotten to history. Which is why we still call the numbers that the whole world uses today Arabic numerals, despite the fact that the guy we have to thank for them wasn't Arab, and the numbers themselves were Hindu. Thanks for watching this episode of SciShow.
So that sort of covers off that, which I wanted to get into for you guys. Now, if you look at this week's lecture slides, that is a big focus for us, measurements. And now, you could argue that one should only be using imperial, right? In Canada, we officially use imperial. But is that really, sorry, not imperial, SI or metric? But should we study imperial? Should we not study imperial? One of the big reasons why we still use or study imperial is we are so integrated into the American system, and they use imperial. So if you stop using imperial, you'll be at a big disadvantage, especially when you're working with the partners south of the border. Now, another interesting thing. So I do a lot of work, or I did a lot of work that was based in drilling. And the entire system, we say we're metric, but we're really not all the time. So in the field, I rarely used metric. Our drilling rods were measured in runs of 5 feet. And our sampling equipment were considered 24 inches or 18 inches. And we measured blow counts in every 6 inches. Why? Because that's how the American system is. So that's an example of how integrated we are. But then we would convert everything. We would convert everything when we're reporting. And so we'll go through a couple of the basics. Measurements and know that how to divide them up. Okay. All right. Jasmine, is it Jasmine or Yasmin? Good to have you here. So we'll keep going. I think we covered these slides. So as we were talking about earlier, the inconsistent systems created problems. So how are you going to measure things and how are you going to work with things if different people are using different systems? And depending on the king or the ruling party of the time, different systems were used. Now, if you say that the yard is a certain person, or let's say it's a person in the royal court, or it's the king's, the measurement from the nose to the end of the hand, well, you're going to have problems. Like that yard is going to change every time you have a new king. Or if you say that 1 inch is 3 barley corns, that's not going to work. Because, every time you put it together, how are you going to make sure that it's standard? And so that's where you got into situations where people like the guy we just heard about, Al-Khwarizmi, put together these systems of measurements and use of numbers, and others came and did the same, so that we ended up with something that kind of looks like this. So our SI units are the official units that we use in Canada. However, in this course and in other courses I teach, we try to learn about both SI and imperial. Now, just remember that the unit of measurement of length is going to be meters. But that's one dimension. And if you're looking at 2 dimensions or area, it's going to be meters squared, length times width. And if you're going to get volume, it's going to be length times width times height. So it's going to be meters cubed. You're going to use grams or kilograms for mass. We're not going to be using time or measurements of temperature, so we don't really have to worry about that. But as you can see, for volume, you've got cubic meters, for area, square meters. You're going to be using a lot of this force. For force, it's going to be newtons. You're not really going to be using meters per second much, although we might touch on it just to get an idea. Another major development when it came to Arabic numerals using the Hindu system was the fact that you could add zeros everywhere. Zero was one of the best things that they ever invented, because now you can deal with numbers that we were previously really struggling to. Now for this course, just remember that if something's a million, it's mega. If it's 1,000, like if you multiply by 1,000, it's kilo. And another thing to remember is you can actually use exponents to discuss or describe a number. Again, if you want to divide, it's deci. For 1/10. For 1,000, it's milli. For 1 million, it's micro. Oops. So this basically adds to that, right? Another thing that's important is that when you're at a site or you're observing anything, you want to be able to understand what is approximately the height of something or have a scale. And that's why knowing the height of a person is about 1.8 meters, or knowing the height of a doorknob is about a meter. And if you take a large step forward, let's say you don't have time to take an accurate measurement, just take a large step forward. For a male, a regular step is about 0.8 of a meter, a lunge is about a meter, and a female, it's about 0.7, depending on your height. Here's a conversion between a yardstick and a meter stick. It's not exactly the same. Now, I know some people sometimes almost act like the meter and yard is interconvertible, but that's not really true. This is where knowing what each means is extremely important. So in 1 yard, how many feet do we have? We have 3 feet. In 1 meter, I have 3.28 feet. So just like the meter is the measurement of distance, or sometimes people use kilometers, multiply by 1,000, or divided by 1,000 to get the kilometers. In imperial, it's feet and miles. So knowing these conversions will be very beneficial to you, helpful to you. And having them handy in a test is going to be your make or break. Turning on. So a centimeter is approximately the width of your finger. Let's say your index finger. While a millimeter is about the thickness of a dime. So it's a good idea to always have a ruler available, just for even small measurements. And I also like to get one of those where you can actually look through and it magnifies. Now, the good news for you guys is that you're not really dealing with having to convert scales and determine areas on a map, which is what we used to do. Now that you've got CAD or you've got GIS, it's not something that you have to do on your own. You can actually get your computer to help you with that. But I still think it's a good idea to have a ruler available or have a measuring tape available. So here's a comparison of what 1 square inch looks like compared to 1 square centimeter. You can see the inches a little bit long. So that's why, like, when you go to the US, say in the winter, and they talk about, oh, well, we're gonna have 3 inches of snow. That's a lot more than what would be 3 centimeters of snow. Now, this is what an area looks like. It's 2 dimensions. Area, when we're talking about area, it's 2 dimensions. So let's just talk a little bit about that. Although you're not going to be dealing with it too much, but it's something to note that we live in 3 dimensions. Or one could argue 4 dimensions, depending on who you ask. And what the context is. So when you talk about 3 dimensions, you're looking at length, width, height. If you want to go into the 4th dimension, you add time. And that's why you'll hear physicists talk about the space. This is the space aspect, and then this is time continuum. Why? Because it's four-dimensional space-time. Do we have a fifth dimension? Does anybody know if we have a fifth dimension? Well, if you guys have heard of Einstein, the way he described gravity in his general theory of relativity, this is gravity curves space and time. And where does it curve it? Into a fifth dimension. And we are going to be using gravity and understanding how gravity works. Why? Why is it important for us? Are we going to get into high dimensions theoretical physics? No, of course not. That is for PhDs and beyond, or very highly sophisticated physics courses. But we do need to know how the gravity is acting at the surface of the Earth. We do need to know how it's acting when it comes to an object. Because your structures are going to be influenced by gravity, and we're going to try to understand how to work with gravity to build structures that do not collapse. The calculations that we're going to do is how gravity is going to be acting on the Earth based on the structures that you design. That's the core of this, especially the first part of the course. And we call that statics, because it's for things that are standing still and not in relative motion. But if you have a scenario like this is going to be helpful to you to consider later on. Make sure you understand the dimensions. What are the widths? Because this is hollow in the center, or this let's just assume that this is a structure that you're trying to determine the center of gravity for later on in the course. Having the knowledge and understanding of what the different dimensions are going to be critical to you. Because if you don't, you will likely have a scenario where you'll have an erroneous answer. Having spatial awareness is going to be helpful to you. Like, what does this mean? So if these are the dimensions, you're 40 centimeters this way, 30 centimeters this way, 20 centimeters this way, and you just want to know what this area or this plane is going to be, the area is going to be easy to find if you understand what these dimensions mean. So this means that this is 30 centimeters long in this way and 20 centimeters high. And to develop the area, it's just 30 times 20. Which is what exactly we've done here, the cross section. It's based on our understanding of spatial attributes of that surface that we want to calculate the area for. Another good thing to have knowledge of or have a good understanding of is converting different unit systems. So a hectare, what is it equal to? 10,000 square meters. Or 100 by 100 meters. In this case, you've got an area 6 inches wide and 4 inches tall. What is its area going to be? So area of a square or a rectangle is always base or width times height. So it's going to be 6 times 4. That should be 24. But if you were to depict it graphically, you would get the exact same answer, or you should get the exact same answer. So this would be, you count these 1, 2, 3, 4, 5, 6, and then you count this out this way, 4 this way, so that's 24. But of course, we trust the math, we trust that the formulas that we're given are correct. And we don't usually depict stuff graphically. We just run the calculation numerically and move forward. Similarly, when we're calculating volumes, 1 centimeter by 1 centimeter by 1 centimeter. So that's 1 centimeters cubed. Extremely important. Now let me press this point here. You have an area. And let's say this is 4 meters and this is 3 meters. I know it's not a good drawing, but please just assume it's a square. So the area is going to be equal to the base times the width, 4 times 3, which is equal to 12. But it's important for you to note that this is in meters and this is in meters. So the unit of the area is going to be in meters times meters, or equal to meters squared. And let's say you were to try to look for a volume, right? Again, a bad drawing, but let's say the height is 2 meters. So the volume is going to be equal to the base times width times height times 224, and in this case, it's going to be meters cubed. For all intents and purposes, you're only going to need to know the basics when it comes to this. But it's good to have that knowledge. Most of you are already quite knowledgeable when it comes to that. So there you go. You got your volume is going to be 6 times 4 times 5. So that's 24 times 5. I guess that's what, 120? Not sure. 24 times 5. Here's another interesting concept, that the liter, even in SI units, is a little bit larger than quart in imperial. Although they're quite comparable, the liter is still a little bit larger in volume. And another interesting aspect is 1 liter contains 1,000 cubic centimeters. 1,000 liters is what we usually have for 1 cubic meter of water. In this case, it's 8 inches by 4 times 5, so that's going to be 8 times 4, 32 times 5. I don't know the exact answer. I think it's 32 times 5 is 150, plus it should be about 160. Another thing, when you're looking at items in 3 dimensions, it's quite key or quite important to know what face you're referring to, what side you're referring to. Okay, so let me now pull up something else for you guys. Another interesting clip. So let's watch this clip about SI units.
I'll tell you a story about a prince you know as Scar and an orphan.
What does the French Revolution have to do with the time NASA accidentally crashed a $200 million orbiter into the surface of Mars? Actually, everything. That crash happened due to an error in converting between two measurement systems, U.S. customary units and their SI or metric equivalents. So what's the connection to the French Revolution? Let's explain. For the majority of recorded human history, units like the weight of a grain or the length of a hand weren't exact and varied from place to place. And different regions didn't just use varying measurements, they had completely different number systems as well. By the late Middle Ages, the Hindu-Arabic decimal system mostly replaced Roman numerals and fractions in Europe. But efforts by scholars like John Wilkins to promote standard decimal-based measures were less successful. With 250,000 different units in France alone, any widespread change would require massive disruption. And in 1789, that disruption came. The leaders of the French Revolution didn't just overthrow the monarchy. They sought to completely transform society according to the rational principles of the Enlightenment. When the new government took power, the Academy of Sciences convened to reform the system of measurements. Old standards based on arbitrary authority or local traditions were replaced with mathematical and natural relationships. For example, the meter, from the Greek word for measure, was defined as 1/10,000,000th between the equator and North Pole. And the new metric system was, in the words of the Marquis de Condorcet, for all people, for all time. Standardizing measurements had political advantages for the revolutionaries as well. Nobles could no longer manipulate local units to extract more rent from commoners, while the government could collect taxes more efficiently. And switching to a new republican calendar with 10-day weeks reduced church power by eliminating Sundays. Adoption of this new system wasn't easy. In fact, it was a bit of a mess. At first, people used new units alongside old ones, and the republican calendar was eventually abandoned. When Napoleon Bonaparte took power, he allowed small businesses to use traditional measurements, redefined in metric terms. But the metric system remained standard for formal use, and it spread across the continent along with France's borders. While Napoleon's empire lasted 8 years, its legacy endured far longer. Some European countries reverted to old measurements upon independence. Others realized the value of standardization in an age of international trade. After Portugal and the Netherlands switched to metric voluntarily, other nations followed, with colonial empires spreading the system around the world. As France's main rival, Britain had resisted revolutionary ideas and retained its traditional units. But over the next 2 centuries, the British Empire slowly transitioned, first approving the metric system as an optional alternative before gradually making it official. However, this switch came too late for 13 former colonies that had already gained independence. The United States of America stuck with the English units of its colonial past, and today remains one of only 3 countries which haven't fully embraced the metric system. Despite constant initiatives for metrication, many Americans consider units like feet and pounds more intuitive. And ironically, some regard the once revolutionary metric system as a symbol of global conformity. Nevertheless, the metric system is almost universally used in science and medicine, and it continues to evolve according to its original principles. For a long time, standard units were actually defined by carefully maintained physical prototypes. But thanks to improving technology and precision, these objects with limited access and unreliable longevity are now being replaced with standards based on universal constants, like the speed of light. Consistent measurements are such an integral part of our daily lives that it's hard to appreciate what a major accomplishment for humanity they've been. And just as it arose from a political revolution, the metric system remains crucial for the scientific revolutions to come.
Any questions from you guys?
How am I already underwater?
I'm in the same boat. I'm in an actual boat because I've been using Grammarly's.
Any questions?
I do have one question.
Yeah, go ahead, Adrian.
The video mentioned the United States was one of three countries who used the units measure, correct?
Correct. That still do.
So what are those other two countries?
Myanmar and Liberia.
Okay, thank you. Sorry, I was just curious.
Yeah, no, it's interesting. That being said, would you not agree that we are still using some imperial in this country? I would say we are a hybrid. I don't think
Yeah,
completely metric. I don't agree with that. I think we're a hybrid. And one of the big problems we're facing as a society recently is what? What is our biggest challenge these days as a country? What would you say?
wow, no,
Would you say
I,
that Trump is our biggest challenge?
maybe, but I think climate change is the biggest issue in Canada.
Yeah, I don't think so. I don't agree with that. I think it's one of the main issues for the whole of humanity, but I think we have bigger problems than climate change right now in the immediate. Because if you look at our economy, one of the reasons why we're still using imperial is because we're so integrated with the American economy. And if we don't get this sorted out with the president, we'll have a lot of economic challenges. Like it's really nice to want to protect the icebergs, but if you can't eat, nobody gives a damn about climate change.
Mm, yeah, you're right.
And also, I'll be very honest with you as an environmental professional, climate change is not going to be dealt with by us. It's going to be dealt with by people in who change the way people are living in countries like India and China. Whatever we do, climate change is not going to be stopped by no matter what Canada does. Even if we become the most perfect zero carbon country on earth, there's no way we're going to impact it. What the way climate change is going to be dealt with is we develop a different fuel source from fossil fuels. That's the only way we're going to get rid of the issues with climate change. And it's inevitable that there will be loss of life and land due to climate change. Humans just don't change until children dying are shown on TV. And even then, sometimes we don't change. It's until we get a different way to develop cleaner energy, or if we find a different source of energy, or if we're able to develop the greener energy systems that they're hoping to develop, which so far we haven't done that good a job on, we're always going to have problems. And then we need countries like India, China, and other emerging major economies, even Pakistan, I would include, to also stop emitting greenhouse gases. Otherwise, no matter what we do, it's only going to be, it's going to make us feel better, but we're still going to have climate change. And the irony is, countries like Pakistan, India, Bangladesh are going to feel the effects of climate change way worse than us. But that's the way of the world, right? People tend to deal with things differently. Like I wish that we were more serious about climate change, but we have other problems that sometimes, like for example, we were using carbon tax, but now they pushed that back a little bit. But yeah, I think until we get a different fuel source, we're going to have problems with climate change. I don't think we're ever going to get away from it. Well, thank you for spurring that discussion. I always appreciate when students give their insights, especially when students like yourselves are thinking about the future, whereas our generation might not have done a good job of that. Jasmine, how do I pronounce your name? Is it Jasmine or Yasmin? And Jeremiah, I think I've got your name correct, right? Okay, good. So go ahead, Jasmine.
It's Jasmine.
Jasmine. So I was just thinking, usually after about 45, 50 minutes or so, I do like to take a short break if that's okay with you guys, and then we'll continue. I think what we've got left to do today is mostly we're going to focus on we're going to continue with prefixes, suffixes, conversions, and then I think we get into significant digits, and that's the end of the class for today, okay? So let's just take a short break, 5 minutes or so, and then I'll see you then. Okay, I guess we should continue on. Hopefully the three of you are back. Thank you for participating live. It's a lot easier because if nobody attends, then I might not even record live. I'll just use an old recording and post it, but it's better this way. I enjoy talking to people. Okay, so continuing on. Now what we'd like to get into is a little bit different. So there's conversion, right? So if something is in meters, how do we convert it to kilometers or decimeters or centimeters? And I'm going to touch upon that a little bit, as well as always have a conversion ready. Like for example, if you've got 26 meters, how are you going to convert that into feet? Well, 1 meter contains or consists of 3.28 feet. So 26 would contain 3.28 times 26. Simple enough. But these things get complicated sometimes for people. Okay, so be very, very careful. What I would just do is, instead of trying to figure out how to go, is maybe just know what the conversion factor is. Have a cheat sheet of the conversion factor present. Always have it present. Now, there's a trick that we can use, or I know we're gonna watch a video from Khan Academy. It'll give us that trick as well. When you have a conversion, let's say you have a number in meters and you want to convert it to kilometers. Which unit is larger? Which unit is larger? This one. So you're going to be converting meters to kilometers. You will always divide. Why? Because it's going from a smaller unit to a larger unit. Vice versa, if you're going from, let's say, meters cubed to centimeters cubed, what are you going to do? You're going to multiply. Why? Because you're going from a larger unit of volume, meters cubed, to a smaller unit of volume, centimeters cubed. That's one way. But you need to have the number ready. Let's take a look at our slides again. One of the nice things about the SI units, which just saw that it came out of the French Revolution or became more popular after the French Revolution. One of the key aspects is you can also have prefixes. Like for example, for meters, you can also have kilometers. It's still an SI unit. For grams, you can have kilograms. Now this is a little bit deceptive. It's mass, it's kilograms, because mass remains the same, but the way we talk about it in our regular life, where it's interchangeable mass and weight, but in reality, in physics, it's not. Especially, let's say if you're working with numbers and you're on a different planet. For all intents and purposes, because we are on a planet with a thin crust, the change in gravity is not enough to warrant that we look at it in a more sophisticated fashion. But in physics, we do. We look at a length and weight, mass and weight as separate. But as mentioned, Newton is what we use, the unit for force or weight. even though somebody might say to me, oh, well, you weigh 194 pounds. That's not really true. My weight is not 194 pounds, but that's how it's measured on the weight scale. My actual weight is 194 times 9.81 meters per second squared. It's kilograms. Actually, it's not 194, it's 89 because that's kilograms, meters per second squared. It is 178 times, I think it's 32.2 pounds, feet per second squared. Here are some of the prefixes that the metric system allows us to use. Mega is for a million, so it's 1 6 zeros times whatever number we have. Kilo is 1,000. Hecto is 10 to the power 2. Deci is 10 to the power minus 1, so it's a tenth. Centi is 100th. Milli is 1,000th. Micro is a millionth. And nano is a billionth. And here are examples of what we were going through just now. So the standard unit of length in the metric system is the meter. How do we convert a millimeter to a meter? You divide it by 1,000. How do you convert centimeters to a meter? You divide it by 100. The conversion factor is important for you to be able to perform these tasks. You should have that on your cheat sheet for commonly used conversion factors. Now, how do you determine what should be on your cheat sheet? Whatever questions are in the assignments, use those conversions, and you might be using those conversions in the test, not in the final, in the test. There's 3 tests, there's no final. 3 equally dispersed tests. So let's take a look. We've got 325 in centimeters. What is it going to be in meters? You just divide it by 100. And it's going to give you the answer. So what I want to do is watch a clip where this person does a really good job of explaining this concept. If you ever get stuck with some of the basic stuff, look up those concepts in what I would refer to as Khan Academy. I think that's what it's called. Here we go. It's about 9 minutes long.
Let's get started. So if I were to ask you, or if I were to say, I have traveled, let's say I've traveled 0.05 kilometers. Some people say kilometers or kilometers. If I've traveled 0.05 kilometers, how many centimeters have I traveled? Question mark centimeters. So before we break into the math, it's important to just know what these prefixes, centi and kilo, mean. And it's good to memorize this, or when you're first starting to do these problems, you could just write them down on a piece of paper just so you have a reference. So kilo means 1,000. Hecto means 100. Deca means 10. You might recognize that from decade, 10 years. And then, of course, you have no prefix, means 1. No prefix. No prefix equals 1. Deci is equal to 0.1 or 1/10. Centi, I keep changing between cases. Centi is equal to 0.01 or 1/100. And then milli is equal to 0.001, and that's the same thing as 1/1,000. And the way I remember, centi, if you think of a centipede, has 100 feet. A millipede, I'm not sure if a millipede has 1,000, but that's the implication when someone says a millipede, because pede means feet. So let's go back to the problem. If I have 0.05 kilometers, how many centimeters do I have? So whenever I do a problem like this, I like to actually convert my number to meters because that's very easy for me. And actually, I'm going to abbreviate this as km. And we can abbreviate this as cm for centimeters. So let's say 0.05 km. Well, if I want to convert this into meters, is it going to be more than 0.05 meters or less than 0.05 meters? Well, a kilometer is a very large distance. So in terms of meters, it's going to be a much bigger number. So we can multiply this times 1,000 meters, and I'll do it over 1 per kilometer. And what does that get? Well, 0.05 times 1,000 is equal to 50, right? I just multiplied 0.05 times 1,000. And with the units, I now have kilometers times meters over kilometers. And the kilometers cancel out. And just so you're familiar with this, you can treat units exactly the same way that you would treat numbers or variables. If you have the same unit in the numerator and the denominator, you can cancel them out, assuming that they're not adding units, you're multiplying units. So you had kilometers times meters divided by kilometers. And that equals 50 meters. And it's good to always do a reality check after every step. Usually when you do this type of problems, you know, okay, if I want to go from kilometers to meters, I'm going to use the number 1,000 because that's the relationship between a kilometer and a meter. And you're always confused, well, do I multiply by 1,000 or do I divide by 1,000? And you always have to say, well, if I'm going from kilometers to meters, I'm going 1 kilometer is 1,000 meters, right? So I'm going to be multiplying by 1,000. I'm going to get a bigger number. So that's why I went from 0.05 and I multiplied it by 1,000 and I got 50. So let's get back to the problem. 0.05 kilometers is equal to 50 meters. We're not done yet. Now we need to convert those 50 meters into centimeters. Well, we can do the same thing. 50 meters times how many? So what's the relationship between meters and centimeters? Well, if we look at the chart, we see it's 100. And the question I'm going to ask you, am I going to multiply by 100 or am I going to divide by 100? Well, it's the same thing. We're going from a bigger unit to a smaller unit. So 1 of a bigger unit is equal to a bunch of the smaller unit. So we're going to multiply. So we say times 100 centimeters per meter. Right? And that just makes sense. There's 100 centimeters per meter. So 50 meters times 100 centimeters per meter is equal to 50 times 100 is 5,000. 5,000. And then the meters cancel out, and you get centimeters. So we have here is 0.05 kilometers is equal to 5,000 centimeters. Let's do another problem. I think the more examples you see, it'll make a little bit more sense. And always try to visualize what we're doing, the scale. Otherwise, it's very confusing whether you should multiply or divide. Let's say I have 422 decigrams grams are a measure of mass. It's 1 gram is actually a very small amount. That you measure, I guess in the metric system they measure gold in terms of grams. And I want to convert this into milligrams. So before we start the problem, let's just do a reality check. Am I going from a bigger unit to a smaller unit or a small unit to a bigger unit? Well, decigrams, that's 1/10 of a gram. And I'm going to 1/1000th of a gram. So there's 2 ways of doing this. We can convert to grams and then convert to the other unit. That sometimes makes things easy. Or we could say, well, how many milligrams is equal to 1 decigram? Well, a milligram, as we see here, is 100 times smaller, right? To go from 1/10 to 1/1000, you have to decrease in size by 100. So we could just say 422 decigrams times 100 milligrams per decigram. And then the decigrams will cancel out. And I'll get, was it 422 times 100? That's 42,200 milligrams. Now, another way you could have done it is the way we just did that last problem. We could say 422 decigrams. We could convert that to grams. So we could say 422, I'm just going to say DGs, although that's not really a familiar unit, decigrams. And how many decigrams are there per gram? And if we're going to gram, 422 is going to be a smaller number of grams, right? So we could say times 1 decigram is equal to how many grams? Well, 1 decigram is equal to, 1 gram is equal to how many decigrams? Well, 1 gram is equal to 10 decigram. And the reason why this makes sense is if we have a decigram in the numerator here, we want a decigram in the denominator here. So if we have decigrams cancel out, so 422 decigrams will equal, that divided by 10 is equal to 42.2 grams. And now we could just go from grams to milligrams. Well, that's an easy one. 1 gram is equal to 1,000 milligrams. So we could say times 1,000 milligram per gram. The grams cancel out, and we're left with 42,200 milligrams. Right? 42.2 times 1,000. Hopefully that doesn't confuse you too much. The important thing is to always take a step back and really visualize and think about, should I be getting a larger number or a smaller number than the one I started off with? I think you're ready to now try some problems. Have fun.
All right, let's go ahead and perhaps try a few more problems here before we move on to the next topic. So let's say we've got 45 square centimeters. We'll just do 1 or 2 of these. So 45 square centimeters. Two meters squared. So remember, 1 centimeter is equal to 0.01 meters. So 1 centimeter squared. So what is that equal to? 1.01. Each multiply the 2, and that will give you a square meter. Essentially, it's 0.01 times 2. Hold on, 0.01 and 0.01 is equal to 0.0001 meters. So 45 centimeters squared is going to be equal to 0.0001 meters times 45, which gives you, let's see, I think it'll be 0.045 centimeters squared. So a quick comment here. Do not forget units in your answers. In your working, I'm not too worried. Do not forget units in your answer. All right, let's see which other. I'm not going to look at. Well, we've got another question here. Convert. This is actually between different systems of units. Convert 20 3 feet into inches and into meters. Convert 23 feet into inches. Remember, 1 foot is equal to 12 inches. So 23 feet is equal to 12 times 23. You can use your calculator, or I'll just do it here. 6, 3, 4, 1, 6, 7, 176. Is that the complete answer? No. Inches. Always include inches in your answer. Okay. Otherwise, your answer is incomplete, and in terms of this course, you will lose marks, but also wherever you're working, there'll be a problem if you don't lose. Okay. The next concept, scientific notations. So when you have extremely large numbers or significantly small numbers, you can use what is known as the scientific notation. And you can express a number in terms of a coefficient, a base, and a power. In this case, the coefficient would be the actual number multiplied by 10 to the power whatever we need to express it. And it comes in really handy when we're talking about, for example, in geological terms or astronomical terms. So like, for example, you've got this number, 123 billion. All you do is you put 1.27 times 10 to the power. So you've got 9 zeros, and then you're putting a decimal between 1 and 2, so you'll have two more for all intents and purposes, you're adding 2 more to the power of 10. So 1.27 is the coefficient, 10 is the base, and 11 is the power. So let's say in this case, how would you express this in a scientific notation? You would simply say 3.45 times 10 to the power. How many decimal places have you moved us over? 1, 2, 3, 4, 5. 10 to the power 5. How would you express 0.45? 0.00000045. You would move this decimal to between 4 and 5. And how many zeros, how many places have you moved it? 1, 2, 3, 4, 5, 6. It's going to be 10 to the power minus 6. And basically all you're saying, basically writing this 0.00, is that 2, 3, that's 5. 5. You're moving this decimal over here. That's all you're doing. It's the same number, and you're multiplying it by 10 and minus 6. Or you're just saying it's 4.5 divided by 1, 2, 3, 1, 2. That's all you're doing. Okay, this is a comma, not a decimal. All right. So then we come to the next main topic of today, and it's basically the final topic of the week. significant digits. Now, we're going to go back to Khan Academy because the way he describes it is awesome. When you're talking about significant digits, there's certain rules that you follow. All non-zero integers or numbers are significant. So, for example, 457 is your number. It has 3 significant digits. Then the next rule is all zeros to the left of the first non-zero digit are not significant. So the zeros before 98 in this number 0.0098 are not significant. The next rule is all zeros between non-zeros are significant. So the zeros between 4 and 5 are significant. So all of these numbers are significant. While over here, only 2 numbers are significant. Rule number 4, all zeros at the end of a number that has a decimal are significant. So these are all significant because it adds to our understanding of precision and accuracy. So this, before we continue, I need to mention this. So let's say you're doing target practice. Let's say you're doing target practice, and this is your target. So there's a concept of precision in science. Let's say every time you shoot, you're getting it here. Let's say you shoot 20 times, they all go here. That's precise because every time you repeat the process, you're hitting the same spot. That's precision. Is that accurate? No. Let's say you're hitting here. That is accuracy. You're hitting the target. I mean, ideally what you want is you want to be precise and accurate every time, but that's not always the case. And this is where the concept of significant digits also helps us to be more precise. Although for me, for all intents and purposes for this course, I don't worry about significant digits, but it is a concept that you will need to be comfortable with. So the last rule, if there's no decimal point at the end, so these zeros are not significant. Okay, so again, here are the basic rules. All non-zero digits are significant. All zeros between significant digits are significant. All zeros, which are both to the right and left, to the right of all non-zero digits are themselves significant. Now, I might have just confused you. So this is why we're going to, again, get the help of Khan Academy. This clip is a little bit shorter than the last one. And so it'll help us.
Let's see if we can learn a thing or two about significant figures, sometimes called significant digits. And the idea behind significant figures is to just make sure that when you do a big computation and you have a bunch of digits there, that you're not over-representing the amount of precision that you had, that the result isn't more precise than the things that you actually measured, that you usually use to get that result. But before we go into the depths of it and how you use it with computation, let's just do a bunch of examples of identifying significant figures. And then we'll try to come up with some rules of thumb. But the general way to think about it is, which digits are really giving me information about how precise my measurement is? So on this first thing right over here, the significant figures are this 700. So over here you have three significant figures. And it might make you a little uncomfortable that we're not including these zeros that are after the decimal point and before this 7, that we're not including those, because it's like, that does help define the number. And that is true. But it's not telling us how precise our measurement is. And to try to understand this a little bit better, imagine if this right over here was a measurement of kilometers. So if we measured 0.00700 kilometers. That same measurement, this would be the exact same thing as 7 7.00 meters. Maybe, in fact, we just used a meter stick and we said it's exactly 7.00 meters. So we measured to the nearest centimeter. And we just felt like writing it in kilometers. These two numbers are the exact same thing. They're just different units. But I think when you look over here, it makes a lot more sense why you only have 3 significant figures. These zeros are just kind of telling you, are just shifting it based on maybe what the units of measurement that you're using. But the numbers that are really giving you the precision are the 7, the 0, and the 0. And the reason why we're counting these trailing zeros is that you didn't, whoever wrote this number didn't have to write them down. They wrote them down to explicitly say, look, I measured this far. If they didn't measure this far, they would have just left these zeros off and they would have just told you 7 meters, not 7.00. Let's do the next one. So based on the same idea, we have the 5 and the 2. The non-zero digits are going to be significant figures. You don't include this leading 0 by the same logic that if this was 0.052 kilometers, this would be the same thing as 52 meters, which clearly only has two significant figures. So you don't want to count leading zeros that are leading zeros before the first non-zero digit, I guess we could say. You don't want to include those. You just want to include all of the non-zero digits and everything in between, and trailing zeros if a decimal point is involved. I'll make those ideas a little bit more formal. So over here, the person did 370 and then they wrote the decimal point. If they didn't write the decimal point, it would be a little unclear on how precise this was. But because they wrote the decimal point, it means that they measured it exactly to be 370. They didn't get 372 and then round down, or they didn't have kind of a roughness only to the nearest tens place. This decimal tells you that all 3 of these are significant. So this is 3 significant figures over here. Then on this next one, once again, this decimal tells us that not only did we get to the nearest 1, but then we put another trailing 0 here, which means we got to the nearest tenth. So in this situation, once again, we have 3 significant figures. Over here, the 7 is in the hundreds, but we got all the way down. The measurement went all the way down to the thousandths place. And even though there are zeros in between, those zeros are part of our measurement because they are in between non-zero digits. So in this situation, every digit here, the way it's written, is a significant digit. So you have 6 significant digits. Now this last one is ambiguous. The 37,000. It's not clear whether you measured exactly 37,000. Maybe you measured to the nearest 1 and you got an exact number. You got exactly 37,000. Or maybe you only measured to the nearest 1,000. So it depends on what, there's a little bit of ambiguity here. If you just see something written exactly like this, you would probably say, if you had to guess, or not guess, if there wasn't any more information, you would say that there's just 2 significant digits. 2 significant figures or significant digits. For this person to be less ambiguous, they would want to put a decimal point right over there, and that lets you know that this is actually 5 digits of precision, that we actually go to 5 significant figures. So if you don't see that decimal point, I would go with 2.
All right.
Based on the examples in the last video, let's see if we can.
That is all you need to know from my standpoint. We've just got a few more slides to work on. We've already, let's take a look at this. To me, there's only one significant digit. This is 5. And in this case, 870,000 is only 2, right? If you look at the rules, follow the rules, right? In this case, how many significant digits? Well, they've actually listed zeros after the decimal. So following the same description that, or the same rules, I think there's 6 significant digits, all right? Any questions about this?
How much significant digits would the third example be?
The third example here.
No, the 0.0305.
So for this one, I would say it's 3. It's 3, 0, and 5. I do not consider the zeros before the 3 as significant.
Thank you.
Okay. So we've already talked about this. Now, if you ask me, I'm not going to go into these slides because what I want to do is I want to mention what I would recommend for you guys for this class. Yes, you should understand significant digits, right? It's a part of the learning. But right now, let's say you're working and you get a number 26.43233. That's supposed to be your answer. Let's say it's square meter. So I would say round up to do decimal places. So this would be 3, right? It's less than 5. So this remains 3. This is 3 less than 5 remains 2. 2 is less than 5. This remains 3. So the answer to me, rounding, would be 26.43 square meters. Let's say you have another number, 78.922. And I want you to round it to not significant, 2 decimal places. So this is 5 or greater, right? So this will become 3. This is less than 5. So this will remain 2. And that's the answer, 78.92 square meters. Now, should you be rounding in the earlier steps of your calculation? Probably not. But if you do, I'm not going to deduct your marks too much. But let's say in the earlier parts, let's say you got a number 782.3322. Typing that in again and again and again can be tedious. But until you get to the final answer, rounding can give you a rounding error, which gets worse and worse and worse as you multiply at each step. At this stage of the course, I'm not going to penalize you or deduct marks too much for rounding errors, but it is something that you at some stage as a professional, as a technologist, you are going to want to avoid in the future. Okay, why? Because lives are depending on your calculations. You don't want to have a situation where your rounding error puts people at risk. Okay, all right, so that's where they're coming from. They want you to be precise and accurate and use significant digits, significant numbers. So next week, what are we doing next week? We'll have a sneak peek because we have a couple of minutes left.
Professor, I haven't mentioned this, but I really like the Batman figurine you have in the background.
Oh, you do?
Yeah.
But what if you have what if somebody you know dressed up as the real Batman?
Oh, I'd get it. Oh, I don't know what I'd do. I'd get really excited.
That was me a few months ago at an event. I actually went and I stole that. I mean, I didn't really steal it. I paid for it, but I acted like I stole it at a convention.
Did you I heard in downtown there was a convention
Yeah,
uh, a
there's
month
one
ago.
every year.
Yeah. Did you end up attending that, Professor?
So this year I've been a little bit busy. I might have been out of the country. I do end up traveling. I might have been in the Bahamas or somewhere. Um, like the more you get to know me, you'll find out that I do travel a lot for different reasons. Like for example, um, I want to go to Fan Expo. I've actually been invited to Fan Expo with some of my outfits. But the problem is this year I'll be in Saudi Arabia. or Egypt or Dubai. I'm not really sure where I'll be during Fan Expo, but I won't be in Toronto. And they've got another big event coming up. I think it's in Niagara Falls for Star Wars. And I might be in Alberta at that time. So, but if I'm here and I'm able to make the time, I will go.
That's good. That's good.
I've actually competed in certain events. Okay. See you next week. And so we talk about why we do these calculations. We go through what loads we're trying to do the calculations for that you're going to be using. If you as a professional student or a future professional, current student, understand why we're performing these calculations, I find that students tend to have more interest. And then we start looking at some of the basics on math that we're going to use to solve our problems. So like Pythagoras theorem and angles. So that's what we're going to be doing next week. Okay. And where did you work in connection with rock bricks? No, it was so I've done drilling in limited drilling in South Asia, but mostly in Ontario and the southeastern United States. It's environmental drilling. It's not drilling for minerals. It's environmental. It's for soil and groundwater. Okay, so the other thing is if you attend this class next week, so the first part of the class would be the lecture, but the second part you work on the assignment. And so while you're working on the assignment, you can stick around, work on the assignment, and ask me for hints, ask me for help. And if you get stuck, I can help you. Okay. Because it's supposed to be an in-class assignment. So the lecture will include time for the assignment. All right, I'm going to stop the recording now so that it converts and I can upload it to YouTube as soon as possible.